Okay, so we have now the wave equation which we derived, and we've shown that uh, this term here is just 1 over the phase velocity squared, and so uh, a solution to this wave equation is a sinusoidal varying function like this, and also any superposition of um, sinusoidal varying functions or harmonic functions, as we'll see in just a little bit. Okay, so let's get back to the question of whether this phase velocity, how this phase velocity is actually related to the velocity of an actual particle when we basically assume that um, as we've seen, that particles have wave-like properties, and so they can be described by a wave function in principle. And now we have learned how the phase velocity of a wave or a wave function is related to um, the frequency and the wave number of the wave, and so we should find out how this phase velocity is related to the actual particle velocity. Okay, so first we can use the de Broglie relationships to to write omega and k. Okay, the two parts in the phase velocity, two terms in the phase velocity. So omega is equal to 2 pi times the frequency, and one of the de Broglie relationships, which we haven't actually talked about much, but it follows from this one down here, is that the frequency um, is equal to the energy divided by Planck's constant. Okay, and the second de Broglie relationship, which we've talked about more, is with respect to lambda. So k is equal to 2 pi over lambda, and that's equal to 2 pi p over h, where we've basically just substituted Planck's constant h divided by p for lambda, which is again the second de Broglie relationship. Sometimes these relationships are actually written in the following way. We can write omega is equal to the energy divided by h bar, and the wavelength is equal to h bar times k, where h bar is just a shorthand for Planck's constant divided by 2 pi. It's another constant. Okay. So now, if we then what we see, right, is that the phase velocity is equal to omega over k, and if we use these relationships here, um, sorry, for this one and this one, for omega and k, we find that omega over k, the phase velocity is equal to the energy divided by the momentum. Okay, so if we look at this in the non-relativistic limit, we find where the energy is equal to just the kinetic energy, 1/2 mv squared, and the momentum is equal to mv, then we find that E over P is just equal to 1/2 v, which is the phase velocity. If we look at this in the relativistic limit, okay, so that's using that. If we look at this in the relativistic limit, okay, where the total energy is equal to gamma times mc squared, gamma is the Lorentz factor, and P is equal to gamma mv, then the phase velocity is just equal to gamma mc squared over gamma v, which in the end is equal to the speed of light c divided by beta, where beta is equal to, as before, v over c. Okay, it's the speed of the particle relative to the speed of light. And so what we see, this makes it very clear that the phase velocity v sub p is actually not equal to the particle velocity. Okay, they're related to each other, but they're not equal to each other. And so as the particle moves, with velocity v, again, it has a wave function somehow that is associated with it, and that that will move with v sub p, and again, v sub p is just not equal to v. Right? So the phase velocity is not equal to the particle velocity.